Good morning, ladies and gentlemen. Welcome to the Fire Risk and Evacuation Analysis course. Today we are going to discuss Lecture 6, Multi-Simulation Risk Analysis. My name is Adam Krasuski and I am lecturer of the Main School of Fire Service. Because I am visiting teacher at the Aalto University, I would like to introduce myself. So I am the officer of the State Fire Service in Poland, but also associate professor at the Main School of Fire Service. My scientific interests are somewhere between environmental engineering and computer science. I graduated also control and industrial electronics and fire safety engineering. For 23 years I've been serving in the State Fire Service in Poland, but also for 19 years I am researching in the section of computer science. I've gained also some commercial experience. I am co-founder of Consultris Ltd company and I am Chief Technology Officer in this company. So, learning objectives related this course. So first I'm going to develop the need and the sense of use of the fire risk assessment. And the second objective which I defined is improving the understanding and feeling of the probabilistic fire risk assessment. And the last one, I'm going to discuss with you tools for the quantitative fire risk assessment. And the outline for the today lecture, first we start with motivation. Why we need a fire risk analysis, why we need probabilistic approach to this. And then, in order to have the same definition, I know you already have lectures related to the fire risk assessment, but I'm going to introduce very shortly this topic. So I'm going to discuss the risk definition and simple risk assessment method. And then we are going towards the probabilistic risk assessment. And within this topic, we are going to discuss Monte Carlo based fire risk modeling and the multi-simulation approach. The multi-simulation approach is the core of this lecture. Then I would like to discuss the AMUX software, which is the implementation of the multi-simulation approach. And finally, we would like to apply our knowledge. So with using AMUX, we are going to discuss some case study and a simple analysis. Okay, so let's start. Okay, let's just start with some question. How to evaluate that building is safe? If we think in a category of perspective-based design, we may say that building is safe if it is compliant with standards and codes. Standards and codes are manifestation of collective knowledge gathered in fire safety domain. During the number of years we collected knowledge which solution, which safety measure are efficient in the number of previous fire. Standards and codes also contain some level of conservatism. So, in other words, there are some safety measure added to be sure that regardless of the geometry or layout of the building, we are still on the safe side. However, the question is much more complicated if we ask in the engineering meaning. How to calculate that the building is safe? Which measure we should use to check the safety of the building? In the fire safety engineering domain, there is a key assumption broadly used in the analysis. This assumption says that we may say that building is safe if evaluable safe egress time AZ is longer than required safe egress time RZ. In other words, the occupants of the building should have enough time to evacuate safely before fire and its condition and its environment makes it impossible. So the idea of the engineering approach to check whether the building is safe or not is calculate AZ, calculate RZ, and then check whether this inequality holds. How we calculate RZ? RZ is the time needed to evacuate from the building. So the general idea is to find most distant place in the building and calculate the travel time from this place to the exit. Evacuation time is not only the travel time, it also contains the other parts, let's say the detection time, pre-evacuation time, alarming time, and others. So the idea is to gather information about each of the part of evacuation time and then sum it up and calculate the evacuation time or RZ. Regarding the AZ, the situation is quite familiar. In engineering approach, we base on some critical value analysis. Okay, so we distinguish some parameters which characterize fire condition. The mostly applied conditions are visibility, temperature, gas concentration, and heat flux. And it is also defined at which height this value should be checked. So in our country, in Poland, we use 1.8 meters to check this parameter. And each of these parameters has its critical value. So if this value is achieved, we may say that the evacuation is no longer possible. And the time when the one of these critical value is achieved is defined as AZ. And the final analysis is to compare the required safe egress time as the time needed to occupants to evacuate from the building, calculate the available safe egress time, add some safety margin, and then judge whether the building is safe or not. And currently the most applied solution or the analysis type to this problem is deterministic analysis. So we base on some scenarios and separate fire and evacuation modeling. So we separately calculate AZ, we separately calculate RZ, add some safety margin, and then compare and check this inequality. But what are the shortcomings of separate fire and evacuation analysis? One of these is that critical value of fire environment can be achieved in the place in the building where there is no people or they have already left. For example, the fire achieved its critical value at the 8th floor and the people are on the ground floor. In the direct understanding of asset and asset analysis, building is not safe because asset is shorter than asset. Yeah, okay. We may say that we are fire safety engineer and we can judge whether achieving the critical value of fire environment and the 8th floor can treat the people that are on the ground floor. In this sense, it seems that the impact of fire on the 8th floor is limited on the people on the ground floor. But the situation is not very simple in each case. As an example, I serve the analysis of the ventilation system in the underground garage. So here we have some layout of one of this floor of this garage, and this is the slice of the value which represents visibility, and this yellow orange color and this dark black color defines the places when the visibility is shorter than the 10 meters. 10 meters is often used as the critical value. Okay, and in this sense, we should judge whether now we should stop the stopwatch. In other words, whether this situation defined as a asset. Evacuation exit in this place is in this place. Yeah? So people have to evacuate to this door. And we have to judge whether there are still conditions for safe evacuation or not. Okay, it looks like that from every place in the garage we can go safely to the exit. Yeah? Maybe here is there will be some problems, but they are still free of smoke road. Yeah? So now we may say, one group of people may say that no, there is no possibilities to evacuate safely, and the other group may say that it is still possible. Okay, let us look at the next slide. So we have now the situation in the garage after 60 seconds, and now we have to judge whether the evacuation is still possible. Okay? So on the other hand, there are much more spaces when the critical value of visibility is achieved, but on the other side there is still path free of smoke. For example, from this much more distant place we can still find the way free of smoke or free of these critical value conditions where the people can achieve this exit to the stairwell, from this place, and so on. So again, we as an expert, the one group might say that the still evacuation is possible and that this is not the asset, and the other group might say that the evacuation is impossible and the asset is far before achieved. Okay, let's complicate a little bit the situation. So still the same garage. Now we have the 72nd of the fire development, and now probably most of us will say that now evacuation is not possible. But probably there will be few experts of fire safety domain who may say that the evacuation is still possible. Yes, we can still find the path or way free of smoke to the exit from any place in this garage. So such an expert judgment depends on the subjective judgment. So we have, let's say, uncertainty, ambiguity in the evaluation of the situation, whether there is possibilities of safe evacuation or not. And this situation is not very good because makes some, let's say, conflict between experts. What is the solution? The solution is the joint fire and evacuation modeling. Yes, so we can run the simulation of fire and evacuation together and check whether the people go through the smoke or not, and then check whether just observing the simulation, whether the evacuation of asset is longer than asset is satisfied. And here we have some example. So this is FDS simulation together with Pathfinder simulation. Here we can observe the people, yes, and here we have the critical value of the visibility. So in this sense, we can judge whether the ASET-RSET analysis is satisfied or not. However, the problem is, if we look again on this simulation, that the people do not find the path free of smoke. They just go through the smoke to the shortest path from the place where they are to the exit. And because this simulation is created just by adding the slices from FDS to the Pathfinder simulation. So such idea, when we just add some reason values from one simulator, fire dynamic simulator, to the evacuation simulator, is let's say a little bit biased, because people rather try to find a path free of smoke. So the solution is the smoke aware evacuation. So the evacuation in the condition when people are aware where the smoke is and try to avoid going through the smoke. They try to find the place where there is no smoke and try to find the exit through these places. Here is an example from other simulator where the people are or the evacuees are smoke aware. So here we have the place when the fire is and the fire conditions are achieved, and so the evacuees try to find the way, the alternative exit, not this the closest one, but the alternative exit through this place. Yeah, and this way we can evaluate whether they have contact with smoke or not. And of course, when we apply the rule of risk-zero approach, so there shouldn't be any situation when people have contact with smoke. Yes, so we judge whether the building is safe or not with the people. If the people had contact with smoke, it is not safe. If they hadn't head contact, it means that it is safe. The assumption that building is safe if the evacuees hasn't had contact with smoke is the zero smoke exposure policy. This zero smoke exposure policy assumes that we accept the solutions applied in the building, the safety measure applied in the given building, if people don't have or hadn't contact with smoke. This zero smoke exposure policy is not very often applied. Even for the separate smoke and evacuation analysis, this acid-earth analysis, the mostly applied approach is minimal smoke exposure. So these critical values, which we discussed in previous slides, are defined on the such level. For example, the temperature is defined at the 60 degrees of Celsius, and this value is not the zero smoke exposure, rather the minimal smoke exposure. And in our case, we can also apply to this smoke-aware evacuation and joint evacuation and fire analysis minimal smoke exposure approach, because people or during the evacuation can have instantaneous contact with smoke or long exposure to the smoke condition. And we are aware that the instantaneous smoke exposure has low impact or marginal impact on the evacuees comparing to the long exposure. So, if we would like to apply for the joint fire and evacuation analysis minimal smoke exposure, we have to define some measure for the exposition to the smoke. And the broadly accepted approach for measuring the effect of the contact with smoke is the fractional effective dose approach. This fractional effective dose can be related to the toxicant or toxic feature of smoke or thermal feature or thermal injury caused by smoke. And for each of this group of effects, we have defined some measure of how to calculate how smoke in the form of toxicant or temperature can affect the people or evacuees. In the case of smoke, we have some equation defined by Purser. Purser distinguished some, let's say, toxicant in this effective dose and defined the fractional effective dose, which consists of fractional effective dose to CO, so the carbon monoxide, and for example fractional effective dose or chlorocyanide and other gases. Also, it takes into account the hyperventilation effect of high concentration of carbon dioxide and also the suffocating effect of low concentration of oxygen. And so this fraction effective dose is the sum of some partial effective doses of the gases which we take as a toxicant and also some irritant gases. And the value which was gathered or fed by the, let's say, consecutive evacuees are then compared with the lethality effect or fatality effect of this concentration on the population. And if the FED value achieved 1, it means that the 50% of the population might die based on the exposure on the smoke. So in the general term, we use the fractional effective dose as a integral within some time period of the exposition, integral of the concentration and some constant related to the given species or elements. And regarding the temperature effect on the body of the evacuees, we have also defined a fractional effective dose which takes into account the radiation heat and the convective heat. And also this is some effect is related to the exposition of the time. So it looks like the joint fire and evacuation modeling, which also takes into account the smoke-aware evacuation and the effect of the smoke on fire environment on human body when it's calculated relating to the fractional effective dose, is the state of the art of engineering analysis related to the evaluation of the safety. So what we have so far? We have joint fire and evacuation modeling, and this approach allows us to check whether the people have the contact in smoke. We have also smoke-aware evacuation, which is very close to the reality where people try to find a way free of smoke during the evacuation. We have also fractional effective dose, which allows us to evaluate the impact or the consequences of contact of people with smoke. So with these approaches, we may have a very good estimation what may happen within defined fire scenario. Okay, but how to define a fire scenario? Yes, how to define in which place in the building we should define a fire region. Which parameters should be set to the fire? Let us consider this on the basis of a very simple layout of the building. For example, for this building, we would like to perform the analysis. So, which room is proper, or which room is the best choice for fire region? This one, this one, this one, or this one? Maybe in order to evaluate the safety efficiently and comprehensively, we should analyze the safety of the building for the definition of fire region in each of these rooms. So one simulation per each room. Okay. In this way, we will be much closer to comprehensive evaluation of the safety of the building. However, is the probability of fire ignition in this room same as the probability of fire ignition in this large room? This room, it seems that this room has a lower probability. For example, because that the area of this room is smaller than the area in this room. So we might expect that maybe the number of people in this room is greater, or the density of fire load density is greater. So the probability of fire ignition in this room may be a little bit higher than in this room. Okay, we have also, let's say this room is corridor. This is not the plain room. Is the probability of fire ignition in this room the same as in this room, even if the area is the same? Probably not, because we might expect that the fire load density on the corridors is much lower than in the plain room. And we might even expect that there is no burning materials or flammable materials on this in the corridor. Behind each fire scenario, there are consequences. And so let us assume that if we define the scenario for each of these rooms, excluding corridor, we have no fatalities, or the fractional effective dose, calculated fractional effective dose, is at the marginal value. But for the fire in this room, in corridor, we have fatalities. So the building is safe or not? We should take into account the fire in this room, or the probability of fire ignition at the corridor is very low, that we should exclude the consequences of the fire with fire origin at the corridor from these consequences. So maybe the probability that fire ignites at the corridor is so low that we shouldn't take into account in our analysis. Without proper handling or explicit handling of probability of such fire, we just don't know. We don't know whether the probability is low enough that we can, or we may exclude this from this fire scenario from the analysis. As we can see, the definition of the fire scenario contains the parameters which are random or uncertain or variable, and the location of fire origin is not the only one parameter. We have much more parameters that are uncertain and variate. For example, doors. Should we keep doors closed or open? Or maybe the worst case scenario, because we are trying to find such a situation, the worst case fire scenario, is when this and this door are open and this closed. We just don't know. Without proper, performing simulation for this scenario and comparing this with other scenario, we just don't know whether this is the worst case scenario or not. So when we try to analyze more and more parameters, we prone to create the number of simulation. The number of simulation includes. And still the problem remains, what is the probability of given scenario? What are the probability of fire ignition in this room and this configuration of opening and closing doors? Of course, the parameters, whether our doors are open or not, do not close our list or set of random or varied parameters. The fire definition or in our simulation also has the number of varied parameters. For example, soot yield, for example, radiative fraction, for example, CO yield, and many others parameters. What is even worse, that so far we have we don't have the continuous parameters. Yeah, it's just discrete. Doors can be open or closed. Fire can be in this room or not. But in the case of fire definition, we have the continuous, let's say, parameters, which can take any value from the set, from the defined set. So, what is the conclusion of our discussion? So, the conclusion is that without proper handling of the probabilities behind the fire scenarios, we cannot judge whether we are sufficiently evaluate the safety, whether we are sufficiently evaluated the safety of the building. Yeah, maybe for the defined fire scenario, we can prove that the building is safe, but we don't know whether there are many other fire scenarios, which in these scenarios we cannot satisfy this ASET approach. So the fire safety seems to be the science of uncertainty and an art of the probability. And as the editor-in-chief of Fire Technology Journal, one of the prestigious journals in our domain, as he said, probabilistic method are the one of the most important tools in the future of fire protection engineering. So in order to evaluate the safety efficiently, we should have consider the probability of given fire scenario, and having in hand also the tools for measuring consequences, we may calculate risk, which is the probability, might be defined as a probability that given type of consequences occur. Now we are approaching risk calculation. We are going to start our discussion related to the risk calculation from the basic definition of the risk. And here the risk can be defined as a statistical expectation value of unwanted event which may or may not occur. And the risk can be calculated as a probability times the consequences of the given scenario. We also have our definition of a fire risk defined by the ISO standard, and the fire risk is the combination of the probability of a fire and a quantified measure of its consequences. So in order to calculate fire risk, we have to have the probability of some consequences, and the consequences should be quantified, so that should be presented in some measurable values. And with this definition, we may say that when there is a risk, there must be something that is unknown or has a known outcome. Because in the first definition, we say that some unwanted event may or may not occur. And in the second definition, we say something about the probability of the fire. And therefore, the risk is somehow the measure or the knowledge about the lack of knowledge. How less or how much do we know about some undefined, unpredicted or unwanted event. But we are going now to concentrate on the risk calculation, and regarding the broadly accepted definition, of course there are some deviation from this definition. Risk is just the probability times the severity of the consequences. So, in order to calculate the risk, for example, the risk of a given building, we need to have the probability and the consequences, some quantified. So we can quantify consequences into, let's say, monetary value. We can quantify the consequences that somebody dies or not. We can quantify the consequences that somebody can be seriously injured, and so on and so forth. And we need to know the probability of such consequences. Okay, the simplest way of the calculation of the risk is to check the probability and the severity of these consequences. So you are or I'm expecting you are in this building, maybe not now, but in normal cases you study in this building, and it may be interesting to calculate the risk of the risk related or behind this building. So from my information from the Google Maps, the building is 3-story educational building, and the floor area of the building is 3,267 square meters. And let's calculate the risk for this building. What we need? Probability of fire ignition. So the probability of fire ignition can be we can take this value from the statistic. Here we have the statistics for Finland. This is the PhD thesis of Kati Tilander, also published in the form of the article. And in this case, we have the educational building, and this is the age category. So we have the probability of fire ignition in this type of building as 3 times to the power, 3 times to 10 to the power to minus 6, but for 1 square meter. Yeah? Okay, so the probability of fire ignition we have, and the consequences. What are the consequences of fire ignition in educational building? Now, educational building we have explicitly mentioned. So when the fire starts, so we might expect that there will be 32,000 euro, because this is per 1,000 euro per fire. And so these are the consequences. Now it seems that we have each of the value needed for the calculation of the risk. So we have the probability per square meter. So this is this 3 times to 10 to the power to minus 6 times the area of one floor. This is this times the number of floors. So the probability that fire ignite in this building per year, what is important, is 2.94 times 10 to the power to minus 2. And the severity or the consequences of such fire is 32,000 euro. So when we calculate this value, so we multiply probability times the consequences, we achieve 940 euro. So this is the risk of such building. Okay, so it seems that the risk calculation is very simple. We just take from the statistic value of probability per square meter, take the consequences, and we have the value. But what is wrong with this calculation? or maybe there is no any problems with this calculation. Let's pause for a few minutes this presentation and let's think about what is wrong with this calculation. Why? Well, let's think whether this calculation is useful for fire safety analysis, for evaluation of safety of the building, or useless. If useless, why? So let's think for 5 minutes about this problem. Okay, welcome again after a short break. I hope that discussion was fruitful and you found numbers of pros and cons related to this simple method of risk assessment. And I guess that one of the cons this approach was that fire safety engineering is mostly concentrated on protecting the life, not the property. Of course, it also takes into account the property protection, but first they try to evaluate whether the building is enough safe for people. And with this approach, when we calculate the expected loss in property, this approach may be good for insurance company to evaluate how much should be fee for the insurance of this building, expecting that the losses in property will be at such a level. However, we as a fire safety engineers, we need to evaluate the consequences of the fire for people, whether this is the death or serious injured. Okay, so maybe this is not a very big problem because we back to the statistics. This is the statistic from same author, and we try to find the average annual frequency of fire death per area, of course. Okay, so once again, what is the probability that during the fire somebody may die in this in our building? Okay, educational building, apartment houses, row and chain houses, detached house. Oh, there is no educational building. There is no because maybe there is no death reported in this building. And if there is no death reported in this building, it means that there is no risk to life. Is it true? If it is true, it means that if we construct a new building, we may remove all the safety measures related to fire because this building is safe enough. Yeah? Is it true? Of course, no. Because here we have the statistics related to the average, let's say, average statistical building. And the average statistical educational building probably has some safety measure, so efficient that there is no death in some period analyzed by this author. But if we create a building without any safety measure and we call them just educational, we may expect that this will be not enough to protect people. So the other arguments against this method will be that we did not evaluate risk for this specific building of environmental engineering of Alta University, that rather some statistical average educational building. And what is the problem with statistical average building? The problem is, for example, that in order to calculate risk for this building, we just use the area. So from the statistic we took the risk per square meter, and then if we would like to calculate risk for our specific building, we just take the area of the building and calculate risk. But there is some problem with this approach. I would like to illustrate this on this problem on this figure. So we have let's say two buildings, A and B, and each of these buildings has the same floor area, 100 square meters. And regarding our approach, these buildings have the same risk, because area is the same, so area times the risk per square meter, we obtain the same value of risk. But we can observe, or we can easily find that this building is more safe than this. Why? Because here we have the exits from this building, because here the distance from most distant place in the building to exit is much more shorter than this. And if the evacuation time is longer and the fire development is same, so our discussed analysis asset might be not satisfied for this building in some cases and satisfied for this building. So just using the statistic to evaluate the risk of the specific building under construction, we fall into some generalities. We fall into, let's say, average value, which not represent correct our building, and we still stay in the statistical building rather than the specific one. Of course, the examples are more if we change, for example, that the shape of the floor should be square, and then we can compare the still other features of the building or compartment have an impact on the risk. For example, the height of the compartment, the higher is, the bigger the container for smoke, and the building is less. Building is more safe. So we need some approach that make our calculation much closer to our specific building instead of statistical one. So one of the approach you already know from previous lectures, this is the, let's say, expansion of the risk calculation to event tree. So instead of looking at our building as let's say some geometry and trying to find the similarities of, let's say, previous building regarding the type, regarding the floor area, regarding the height of the building, and so on, let's look at our building with using other approach. Namely, let's consider the safety, taking into account the safety measure applied in this building. So in this case, we may evaluate the risk of the specific building, taking into account safety measure applies, and also the probabilities that they may fail. For example, here we have some exemplary event tree. So we have the probability that fire starts in some location, and the probability that there will be manually suppressed, yes, and the probability can be from statistics. Then if there are sprinkler system, the probability that the sprinkler system failed. And then if the sprinkler system failed, the effectiveness of the venting system, the probability that it will operate correctly and remove the smoke, and the other barriers are effective or not. And on the leaves of each of these, let's say, branches of this event tree, we have some scenarios and we have some consequences. And the final risk of the building with using this approach is the sum of the probability times the consequences of each of these scenarios. And the final value of this is presented. So the event tree brings us a little bit closer to our specific building, yeah? But still some problems remain. Namely, the event tree does not model the spatial-temporal relationships. So not only it is important whether the sprinkler system operates or not, but also the time related, for example, to the evacuation time. Yeah, because maybe the sprinkler system will operate too late and there much too smoke will be produced, and of course the people will be unable to evacuate. So the time relationships, so the timetable between each of these course of action during the fire, but also spatial relationships, yeah? Between, let's say, whether the smoke went on the evacuation route or stay in some room, whether there are people in this room, whether this is only one way of evacuation for people, and so on and so forth. And we can use for this spatial-temporal relationship the model fire and evacuation model, which we discussed in our previous slides. But again, we close the loop, the problem of the definition of fire scenario. So again, our approaches can be used in order to calculate risk. Our approaches, for example, fractional effective dose, can be used to evaluate the consequences in the fed value. But still, there is no possibilities to evaluate the probabilities of given fire or probabilities of given fire parameters. Yeah? So the problem of fire scenario, or the problem of the probability of given fire scenario, still remains. And it seems that there is no other way to calculate risk. So we have the consequences, but now we have to calculate the probability of each of the scenario. So, for example, we can perform each of the combination. For example, for the doors, we can create the fire scenario and calculate this in our fire at evacuation model. So we can calculate for each of the possible fire scenario, perform the simulation, and then try to find and group according the consequences, and try to find the probability of each consequences. But this is very laborious task, so we need a number of simulations. And the second problem is that, again, we don't know whether the probability fire ignition in this room should be the same like in this room, or in this corridor compartment should be the same. So just draw randomly and treating as each probability as equal is not very good approach.